Swayam Prabha. Digital India. Educated India.
So, next we are going to discuss the Miller-Rabin test, that is, if you take n minus 1, then we can write m into 2 power k. So, this is the behind of Fermat primality test. So, if you take a power n minus 1, then it can be written as a power m into 2 power k, which is equal to a power m the whole power 2 power k up to k times we can do that. So, Miller-Rabin test needs from step 0 to k minus 1. Now, we have to write the code. The pseudo code for Miller-Rabin test is a Miller-Rabin test of ordered pair n comma a, where n is a number and a is a base, and find m and k such that n minus k equal to m into 2 power k. If t equal to a power m under modulo n, and if t is plus or minus 1 and return a prime, for I is tends to 1 to k minus 1, where k minus 1 is the maximum number of steps. If t is equal to t square under modulo n, if t is plus 1 return a composite and t equal to minus 1 return a prime, therefore, we have to return a composite. Next, does the number 56 pass the Miller-Rabin test? Now, you take the base 2. So, let 561 minus 1 you take it, and this can be expressed 35 into 2 power 4, which means m equal to 35 and k equal to 4 and a equal to 2. So, initially we have to test 2 power 35 under modulo 561. So, the resultant is 263 under modulo 561, when k equal to 1 and the t equal to 263 square under modulo 56. So, 166 under modulo 561 and k equal to 2. We have t equal to 166 square under modulo 561, which is equal to 67 modulo 561, when k equal to 3, t equal to 67 square modulo 561 equal to 1 modulo 561, which is a composite. So, this way we can test the Miller-Rabin test. Now, we already know that 27 is not a prime. Let us apply the Miller-Rabin test. So, with base 2, we have 27 minus 1 equal to what? 26, that can be 13 into 2. So, 13 into 2 power 1, which means m equal to 13 and k equal to 1 and a equal to 2. So, in this case, because k minus 1 is 0, and we should only do the initial steps t equal to 2 power 13 under modulo 27. The value is 11 under modulo 27. Therefore, the algorithm never enters the loop, so it returns a composite. What we know that 61 is a prime. Let us see if it passes the Miller-Rabin test. We use the base 2. Now, we take 61 minus 1 is 15, 60. 60 can be written as 15 into 2 square, and you take m equal to 15 and k equal to 2 and a equal to 2. So, initialization of t equal to 2 power 15 into modulo 16, which is equal to 11 under modulo 61. Therefore, k equal to 1. Therefore, t equal to 11 square under modulo 61. Therefore, we have the value of minus 1 under modulo 61 a prime and the Miller-Rabin test. Next, recommended primality test. Today, one of the most popular primality test is a combination of the divisibility test and Miller-Rabin test. Then the solution is perform the divisibility test of the values of 4033 is a composite, 37 into 108. Does it passes the recommended primality test? So, the solution is perform the divisibility test first. So, the numbers are 2, 3, 5, 7, 11, 17 and 23 are not divisors of 4033. Perform the Miller-Rabin test with the base 2. So, 4033 minus 1 is 63 into 26, which means m is 63 and k is 6. So, initialization t is identically equal to 2 power 63 under modulo 4033, which is equal to 3521 under modulo 4033. Therefore, when k equal to 1, then t equal to t square equal to identically equal to 3521 square under modulo 4003. So, the value of this one is -1 under modulo 4033, which is passes. So, but we are not satisfied, we continue with another base 3. So, t you take it initially 3 power 63 under modulo 4033, which is equal to 3551 under modulo 4033. Let k equal to 1. So, t equal to t square, which is equal to 3551 square under modulo 43, which is identically equal to 2443 under modulo 4033. Let k equal to 2, t equal to t square equal to 2443 square under modulo 4033 is identically equal to 3442 under modulo 4033. When k equal to 3, t equal to t square, which is identically equal to 3442 square under modulo 4033 is identically equal to 2443 under modulo 4033. When k equal to 4, t equal to t square equal to 2443 square under modulo 4033 identically equal to 3442 under modulo 4033. When k equal to 5, t equal to t square, which is identically equal to 3442 square under modulo 4033 identically equal to 2443 under modulo 4033, which is failed. Therefore, it is a composite. Next, we are going to discuss the factorization. Factorization has been the subject of continuous research in the past. Such research is likely to continue in the future. So, factorization plays a very important role in the security of several public key crypto system. See the next unit. So, the topic discussed in this section are fundamental theorem of arithmetic, and then factorization method, Fermat method, polar p-1 method, polar row method, more efficient methods. Now, the fundamental theorem of arithmetic is n into p1 power e power 1, p2 into e power 2, p3 into e power e3 and p4 into ek. Now, the greatest common divisor of a into product of prime powers a and b, and then already we discussed the GCD of ab, which is can be p1 of whole power minimum of a1 b1, b2 into minimum of a2 b2 and so on, pk into minimum of ak bk. We already discussed that, we have to recollect and then incorporate. Least then common multiplier is nothing but a into p1 power a1, p2 power a2 and so on, pk ak, and b is nothing but b1 power p1 power p1, p2 power p2 and so on, pk ak. Therefore, the LCM of this can be expressed p1 into maximum of a1 b1, p2 into maximum of a2 b2 and so on, pk of maximum of ak bk. So, we have to do that the LCM into GCD of two numbers is equal to a cross b. Now, we have a trial division method for a pseudocode for trial division factorization. For the trial division factorization of n, when n is a number to be factored, if a is 2 while a is less than or equal to root n, and while n under modulo a equal to 0, therefore, the output is a, and n is equal to n divides a, therefore, a is a plus 1. If n is greater than 1, the output is n, therefore, n has no more factors. Now, we have a problem, use the trial division algorithm to find the factors of 1, 2, 3, 3. So, we run a program based on algorithm and get the following 1233 is equal to 3 square into 137. Next, use the trial division algorithm to find the factors of 1, 5, 2, 3, 3, 5, 7, 7, 8, 4. The solution is we run a program based on the algorithm and get the following like this number can be expressed the product of prime powers like 2 cube into 3 square into 13 into 37 into 43987. Now, we have a Fermat method of finding the equation n equal to x square minus y square. This is the difference of 2 square equal to n. So, n can be expressed the product of two numbers a b, and a is equal to x plus y and b equal to x minus y, the product then x square minus y square comes. Then by method of pseudocode of Fermat factorization, like Fermat factorization of n, if n is a number to be factored, and check it out, x is root n, and while x is less than n, check it out. And then we have a loop x square minus n, where w is a perfect square and y is equivalent to root w, and a choose x plus y and b x minus y, and return a and b. So, that x equal to x plus 1, you have to loop formation do that, and finding the values of all, so that you can have a possibilities of pseudocode for the Fermat factorization. Next, Pollard p minus 1 method is nothing but p is a greatest common divisor of 2 power b factorial minus 1 comma n. So, the pseudocode of this p minus 1 factorization is nothing but when a equal to 2 and e equal to 2, while e is less than or equal to b, then a is a power e under modulo n and e is e plus 1. Therefore, where p is equal to the greatest common divisor, so a minus n comma n, and if p lies between 1 to n and return, it fail, and then go ahead once again you check it out, the polar form of p minus 1 factored. Now, we have a problem using this algorithm and check it out these values, and you can generate the corresponding factors. Use the polar p minus 1 method to find the factor of 57247,159 with the bound b equal to 8. So, we run the program based on the algorithm and take the value of p equal to 421. As a matter of fact, 57247,159 is nothing but 421 into something will come, that is why you have to take an p. So, note that 421 is a prime and p minus 1 has a no factor greater than 8. Therefore, 421 minus 1 equal to the product of prime powers is 2 square into 3 into 5 into 7. So, this is the technique we can use for the recurrence of polar row successive numbers. You start with x1, x2 and so on, xi plus 1 and xi plus 1 to I plus j, and then I plus 1 j, then one check it out xi, like that go on. So, that we can check the round off this one stage, and then successive numbers we can generate it. So, this is the algorithm for finding the polar row method. Polar row factorization n comma b design, when x is equal to 2, y equal to 2 and p equal to 1. When p equal to 1, then check it out the modulo of n of x, f of x, and f of y under modulo n of n, you have to check it out, and then the greatest common divisor of x minus y comma n is p, you have to do that and return p, so that p equal to n, the program has failed. So, next we have a problem related to this, that is, assume that there is a computer that can perform 2 power 30 almost 1 billion bit operation per second. What is the approximation time required to factor an integer of size? Number 1, 60 decimal digits, and number b, 100 decimal digits. So, solution is the number of 60 decimal digits as almost to 200 bits. So, the complexity is then or 2 power 50. With 2 power 30 operation per second, the algorithm can be computed to 2 power 20 seconds or almost 12 days. So, number 2, the number of 100 decimal digit as almost 300 bits. So, the complexity is 2 power 75. With 2 power 30 operation per second, the algorithm can be computed to 2 power 45 seconds many years. So, we have written a program to calculate the factors of 434617. The result is 709, and 434617 equal to 709 into 613. Now, value of x comma y in example 933 when x equal to 2 and y equal to 2 and p is 1. So, similarly, if you go for x equal to 5 and y equal to 26, so we have p 1, and proceeding in this way like that, right, then we have a corresponding 68775 and y value 16309, then we have a p value is 709. So, this way we can calculate the factor of 434617. Now, we have to more in efficient method is quadratic sieve method. The method uses a sieving procedure to find the value of x square under modulo n. So, order of e per c, where c is approximately equal to ln n of ln n of the whole power 1 by 2. Next, we have a number field sieve. The method is used to sieving procedure in the algorithm. So, the ring structure is to find x square is identically equal to y square under modulo n. Then order of e per c, where c is approximately equal to 2 into ln n whole power 1 by 3 of ln of n whole power 2 by 3. Next, we have a problem. Assume that there is a computer that can perform 230 almost 1 billion bit operation per second. What is the approximate time required for this computer to factor an integer of 100 decimal digits using one of the following methods, using the quadratic sieve method and number field sieve method? A number with 100 decimal digit almost 300 bits, therefore, n equal to 2 power 300. So, ln of 2 power 300 is equal to 207, and ln of 2 power 300 equal to 5. So, a can be written as 207 whole power of into 5 power of, which is equal to 14 into 2.23 is approximately equal to 32 into e power 32. So, e power 32 by 2 power 30 is, it takes 20 hours. Similarly, for second one, 207 whole power 1 by 3 into 5 power 2 by 2 is 6 into 3 is 18 approximately, e power 18. So, e power 18 by 230 is approximately equal to 6 seconds. Now, we have a Chinese already we come across, and related to further analysis in a cryptograph. The Chinese remainder theorem is used in the set of congruent equation with one variable, but different moduli which are relatively primes as shown in below. So, the following is an example of the equation with different moduli. X is identically equal to 2 under modulo 3, x is identically equal to 3 under modulo 5, x is identically equal to 2 under modulo 7. So, the solution to this set of this equation is the moment the answer the set x is identically equal to 23 is identically equal to 2 under modulo 3, and 23 is identically equal to 3 under modulo 5, 23 is identically equal to 2 under modulo 7. So, the solution to the Chinese remainder using the first capital M. Capital M is a product of the numbers given m1 into m2 and so on mk, and capital M1 is equal to capital M by m1, m2 equal to m by m2 and so on. Find the multiplicity inverse, calculate, and corresponding modulo, and the solution of simultaneous equation arrived. This is the general formula for finding x equal to a1 into m1 into m1 inverse and so on, ak into mk inverse under modulo m. So, for example, you take x equal to x is identical to 2 under modulo 3, x is identical to 3 under modulo 5, x is identical to 2 under modulo 7. Then capital M is a product of 3 into 5 into 7 is equal to 105. Capital M1 equal to 105 by 3, M2 is 105 by 5, and M3 is equal to 105 by 7. So, that M1, M2, M3 can be determined, and find the inverse of this. So, that simply substitute in this previous formula, you can get the values of x equal to identically equal to 23 under modulo 105. So, similarly we can calculate the another example, find an integer that remainder is 3 when divided by 7 and 13, but it is divisible by 12. So, we can write mathematically the form of the 3 equation. X is identically equal to 3 under modulo 7 and x is identical to 3 under modulo 13 and x is identically equal to 0 under modulo 12. So, it follows that we find that x is equal to 276 already we discussed. So, that simply multiply 7 into 13 into 12 and then we have to calculate m1, m2, m3 and then whether it is divisible by 12, then we have a quotient and remainder. According to that we can find the value of x. Suppose we calculate z equal to x plus y, where x equal to 123 and y equal to 334, but our system accept only the number less than 100. Therefore, we have to do with the help of x is identically equal to 24 under modulo 99. Then similarly x equal to 25 identically to 25 under modulo 98, x is identical to 26 under modulo 26, similarly y given. Therefore, adding each congruence corresponding to the y, so that x plus y will come and simplify, you can get the value corresponding to z in terms of what corresponding moduli of 69, 99, 99, 98, 97 respectively. So, now 3 equation can be solved using the Chinese remainder theorem to find z. One of the acceptable answer is z equal to 457. So, now we are going to discuss the continuation of congruences. Next we have quadratic congruences. In cryptography we also need to discuss the quadratic congruences, that is equation of the form a2 x square plus a1 x plus a0 is identically equal to 0 under modulo n. We limit our discussion to the quadratic equation in which a2 is equal to 1 and a1 equal to 0, that is the equation of the form x square is identically equal to a under modulo n. So, the topic to be discussed in this section is quadratic congruence modulo a prime and quadratic congruence modulo a composite. Now, the quadratic congruence modulo a prime, we first consider the case in which modulo is a prime. Now, the equation x square is identically equal to 3 under modulo 11 has 2 solutions, and x equal to 5 under modulo 11 and x equal to minus 5 under modulo 11, but minus 5 is not equal to identically equal to 6. Note that minus 5 is also identically equal to 6 under modulo 11. So, the solution are actually 5 and 6. Also note that these 2 solutions are incongruent. And next example, the equation x square is identically equal to 2 under modulo 11 has a no solution. Therefore, no integer x can be found such that its square is 2 under modulo 11. Now, quadratic residue and non-residue in the equation x square is identically equal to a under modulo a is called a quadratic residue. If the equation has 2 solution, a is called a quadratic non-residue if the equation has no solution. Next, there are 10 elements in integer modulo 11, exactly 5 of them are a quadratic residue and 5 of them are non-residues. In other words, integer modulo 11 is divided into 2 separate sets. One is called it as quadratic residue and quadratic non-residue as shown in the figure. Division of integer modulo 11 elements in quadratic residue and quadratic non-residues of integer modulo 11 is 1 to 10, and then quadratic residue set is 1, 3, 4, 5 and 9, whereas quadratic non-residue set is 2, 6, 7, 8, 10. Therefore, each element has a square root and here no element has a square root. Next, Eulerian criterion, if a is power p minus 1 by 2 is identically equal to 1 under modulo p, if a is a quadratic residue under modulo p. If a power p minus 1 by 2 is identically equal to minus 1 under modulo p, a is a quadratic non-residue of p. To find out if 14 or 16 is a quadratic residue in integer modulo 23, we calculate 14 power 23 minus 1 by 2 under modulo 23 is 22 under modulo 23, which is equal to minus 1 under modulo 23 is a non-residue, and 16 power 23 minus 1 divided by 2 under modulo 23 is 16 power 11 modulo 23 is 1 under modulo 23 is a residue. Now, solving a quadratic equation under modulo A prime, we have a case p equal to 4k plus 3 is a number, we split it in the form of 4k plus 1, 4k plus 3. So, if x is identically equal to a power p plus 1 by 4 under modulo p, then x can be expressed as minus of a power p plus 1 by 4 under modulo p. For the equation, solve the quadratic equation, x square is identically equal to 3 under modulo 23, x square is identically 2 under modulo 11, and x square is identically equal to 7 under modulo 19. Now, we have a solution, x equal to plus or minus 16 under modulo 23, therefore, root 3 is identically equal to plus or minus 16 under modulo 23 for the first case. For second one, x square identically equal to x equal to root 2. So, root 2 under modulo 2011 has no solution, and x square is identically equal to 7, and then x equal to root 7. So, root 7 having that plus or minus 11 under modulo 19. So, we have a solution. Like that we have to do the quadratic residue. Next we have a quadratic congruence modulo a composite. So, decomposition of congruence modulo a composite. Let us start with x square is identically equal to a under modulo n, therefore, n can be written as product of primes. So, x square you check it out a1 under modulo p1, x square identically equal to a2 under modulo p1, and x square is identical to ak under modulo pk. So, that we have a solution of x1, x2 and so on xk. Now, assume that x square is identically equal to 36 under modulo 77. So, 77 can be expressed 7 into 11. So, we can write x square is identically equal to 36 under modulo 7 is 1 under modulo 7, and another way x square is identically equal to 36 under modulo 11 is 3. Therefore, we have two possibilities of this. So, the answer is x equal to identically equal to 1 modulo 7, and x equal to identically equal to minus 1 under modulo 7, and x is identically equal to 5 under modulo 11, and x is identically equal to minus 5 under modulo 11. So, we can make 4 sets of equation out of this. Step 1, x is identical to 1 under modulo 7, x is identical to 5 under modulo 11 is one step. The second step, 1 and minus 5, third step minus 1 and 5, fourth step minus 1 minus 5. So, these are all the 4 cases. So, the answer is x equal to plus or minus 6 and plus or minus 27. Now, for the complexity, how hard is it to solve the quadratic congruence modulo a composite, to solve the quadratic congruence modulo a composite. The main task is a factorization of modulus. In other words, the complexity of solving the quadratic congruence modulo a composite is same as factorization a composite integer. So, we have seen if n is very large, the factorization is infeasible. Therefore, solving a quadratic congruence under modulo a composite is a hard, has a factorization of the modulus. Next one is exponentiation and logarithm. Suppose you take y equal to a power x, so x can be expressed log y base a. So, this section we have to discuss exponentiation and logarithm. So, the fast expansion is the idea behind the square and multiplied method, that y equal to a power of the structures x suffix nb minus 1 plus into 2 power nb minus 1 plus x suffix nb minus 2 into 2 power nb minus 2 and so on 2 power 0, in which xi is 0 or 1. Therefore, we have to calculate in the packet of separate like this, and then for example, you take a power 9. So, a power 9 can be written as 101 bits, you have to write it, that is bits what we have written in the above. So, it becomes a power 8 into 1 into 1 into a. So, this way we can express the corresponding bit base to the value of a power 9. So, the corresponding pseudocode of square and multiply algorithm is the square and multiply a x n is y take 1 start, and then y I varies from 0 to -1 and x I equal to 1, and y is a into y under modulo n. Therefore, a is a square under modulo return y. Next, to show the process for calculating y equal to a power x using the algorithm previous one, for simplicity the modulus is not shown. This case x equal to 22 converted into binary base 2, the exponent has 5 bits. So, we have to demonstrate a power 22 using the square and multiply. Suppose a square you take it, and then we have multiply with this into x power 4 equal to 1, and then a power 16 square, and then square 8 and 4 and then 2 and 1. So, this way we have to do, and another one is this way you have to a power 6 a power y equal to a power 6 corresponding the value coefficient you have to take it. So, we have the bits corresponding to this is x4 is 1, x3 is 0 and x2 is 1 and x1 is 1 and x0 is 0 corresponding to binary bits. So, 1 0 1 1 1 0 corresponding to this we can write it. So, we have a corresponding equation demonstrated in the square. So, calculate 17 power 22 under modulo 21. So, what we have to do is a equal to 17 square and under modulo 21 is take it, and then value is 16. So, 16 can be expressed 1 into 16 modulo 21, therefore 16, and I equal to what 0 1 2 3 4, the xi is corresponding, the bits you have to write it 1 1 0 1 initially 0. So, that a power 16 under modulo 21 is 4, and then a equal to 4 square under modulo 21 is 16, and a equal to 16 square under modulo 21 is 4, that is initially squaring. Therefore, we can write in terms of the expression of exponential way. And then what about 21 power 24 under modulo 8, then you try. In cryptography, we also need to discuss modulus algorithm. So, the exhaustive search is the model algorithm is model algorithm of a y n and 1 to n minus 1. So, y equal to a power x under modulo n return x and then fail and then go ahead, then we can get it. So, this is the way we can find the powers of integer under modulo 9, and we have a sort of the table, and then we have to express the corresponding powers, and then 2, 4, 8, 16, once again it start with cyclically 13, 17, 7, 14, 9, 18, 17, 15, 11, 3, 6, 12, 5, 10 like that. Next we have order of the group. What is the order of the group? So, integer modulo 21 you take, so or phi of 21 take, phi of 21 in terms of multiple function is phi of 3 into phi of 7, which is equal to 2 into 6 equal to 12. There are 12 elements in this group. Therefore, 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19 and 20. So, they are relatively prime with the 21. Find the order of the element of integer modulo 10. So, phi of 10 equal to 4 elements. So, we can find order of the each element by trial and error. Therefore, 1 power 1 is identically equal to 1 under modulo 10. Therefore, order of 1 is 1. 3 power 4 is identically equal to 1 under modulo 10. The order of 3 is 4. 7 power 4 is identically 1 under modulo, therefore order of 7 is 4. Like that, 9 square is identically equal to 1 under modulo 10, therefore order of 9 is 2. So, next we are going to do with the Euler's theorem, an order of element in the previous with the example. So, I equal to 1, 2, 3, 4, 5, 6, 7 you take it, and A1 3, 4, 5 corresponding we have the order of 1, 3 have I equal to 2 corresponding order, 5 we have order corresponding I equal to 2 is 1, 7 we have order corresponding to like that. So, we can find out the order corresponding to this element. Next one is primitive root. If integer modulo of n, when the order of element is same as the phi of n, is called a primitive root of the group. So, the table 9.4 shows that no primitive root in the integer modulo 8, because no element has the order phi of 8 equal to 4. Therefore, the element are all smaller than 4, and showing that the a power I is identically equal to x under modulo 7. Therefore, in this group phi of 7 equal to 6. For example, I varies from 1, 2, 3, 4, 5, 6 corresponding A1 1, 2, 3, 4, 5, 6. Therefore, the primitive root corresponding this we can easily calculate what are all the roots of this equation. Next, detailed explanation we will discuss next unit, call it as a group theory, but here in terms of primitive we need an integer modulo 4 or integer modulo n, and as a primitive root if n is 2, 4 and p power t or 2 power p power t. So, for which of value of n does the integer modulo n have a primitive root 17, 20, 38 and 15. So, for integer modulo 17 as a primitive because 17 is a prime. For 20 there is no primitive because 20 is not a prime. For 38 as a primitive root because 38 can be expressed 2 into 19 and 19 is a prime and 2 is a prime. Whereas 50 has a primitive root and 50 can be written 2 into 5 square, therefore 5 is a prime. So, in this group the integer modulo has any primitive root, the number of primitive root is phi of n. Now, we have a cyclic group. If G is a primitive root in this group, therefore, having the generator G1, G2 and so on G power phi of n. So, it has a primitive root because phi of 10 equal to 4 and phi of 4 equal to 2, therefore, phi of 10 equal to 2. So, it can be a primitive root 3 and 7, then we can create the whole integer modulo 10 having the primitive root. When G equal to 3, G power 1 under modulo 10 is equal to 3, because 3 under modulo 10 is 3, 3 square under modulo 10 is 9, 3 cube under modulo 10 is 7, 3 power 4 under modulo 10 is 1. Similarly, G7 we have to calculate so that we have order and a primitive root. So, in this way the cyclic group, if it has a primitive roots and it has a cyclic. So, we will discuss deeply on the group theory. And next one is a discrete logarithm. We have a property, the property in integer modulo p, its elements include all the integer from 1 to p minus 1. It always has a primitive root. If it is cyclic, then the phi of the values of x from 1 to phi of n is p minus 1. So, the primitive root can be thought as the base of the logarithm. So, solution to modular logarithm using discrete logarithm for g equal to integer modulo 7, y equal to 1 to 6 and then x equal to L 3 into y. So, we have discrete logarithm. Next, find x in each of the following cases. 4 is identically equal to 3 power x under modulo 7, 6 is identically 5 power x under modulo 7. So, according to the tabulation of a discrete logarithm, 4 is identically equal to 3 power x under modulo 7. Therefore, x equal to L3 base 4 or log of 4 base 7, modulo 7 is 4. Therefore, 6 equal to 5 power x under modulo 7 is same as x of log 6 base 5 under modulo 7 is 3 modulo 7. Now, using the properties of discrete logarithm, we have a comparison of traditional and discrete logarithm. If log 1 base a is 0 and L1 base g is 0 under modulo phi of n, that is the difference between traditional logarithm and discrete logarithm. So, log of xy equal to log x plus log y, here the same way log xy equal to this under modulo phi. So, same way using this, and discrete is based on the Tottian function. Now, using algorithm based on discrete. So, the discrete logarithm problem has the same complexity as factorization problem. So, there ends the ideas of logarithmic types in unit 2.